In the previous class, we have started reviewing the vector algebra, and I have emphasized or I have explained why we want to review the vector algebra, because immediately after this, our formulations, our derivations, and expressions will be full of vectors. It will be vector or scalar, and then there are some operations that you need to be aware of or that you need to review. So for that reason, I said we will take our time out to digress a bit and review the vector algebra that we feel is important and central to understanding proper formulations of the governing equations. And we have started, before with the definition, vectors, what are scalars, and their representations. And then we identify a vector as having three properties. It can be represented magnitude and direction. The length of the arrow gives the magnitude. It has a head or sense, which defines the direction it is moving, forward, backward, and what have you. And then you have the direction inclined to any reference axis, either horizontal or vertical. And this is the tail. Okay? So any vector can be represented like this. And we looked at multiple choice question where we were asked to multiplication of a vector by a scalar will never change the vectors. What is the answer to this? Sense. Okay. This multiple choice, we took it the last time I was here. So I'm just recapping and going over what we did. So what is the answer to this? Sense. If this vector A is multiplied by a scalar minus 1 to have minus A, right? How will it look like? The sense, not direction. This is the direction. Instead of going this way, it will go that way. Has the sense not changed? Huh? What about this one? This is a vector A being multiplied by a scalar, a negative scalar minus 1 to have minus A. So if this is A, then this is minus A. This is the sense for A. For minus A, this is the sense. Did we change the sense or no? Has it changed? Huh? The sense did not change. Did you really? I think I uploaded this presentation in the class WhatsApp group, right? Did you review it? Did you review it? Good morning. Though it's immaterial whether you review it or not, but I'm pretty sure that most of you here were present the last time. I just finished explaining the different components of the vector representation. The tail, this is the sense, and this is the direction. And I was just asking the same question we deliberated and discussed extensively in my last class. Yet you are behaving as if this is the first time you are hearing this. Even after showing exactly that the sense changed. This is the sense for A, when multiplied by negative scalar, it changed the sense, yet you are still saying that the sense did not change.
If I could recall, last lecture we had introduced direction.
What?
Most of us answered direction did not change. And you said the correct answer is sense.
Thank God everything is recorded. So even if it's a court of law, when you go back and listen to our recorded lecture, which I believe I uploaded, I suppose so, didn't I? I never.
The correct answer is sense. The last presentation.
I couldn't have done that. I couldn't have done that. I couldn't have done that. Unless, of course, something happened to my sense as well. If something has happened to my sense, then that's the only reason I can give the answer to be sense. But if nothing happened to my sense, then I couldn't have said that the correct answer is sense. I couldn't. Did I say that the correct answer is sense? I didn't leave the question open. We deliberated. I asked for your opinions. Some chose magnitude, some chose sense, some chose direction. And then I analyzed each one of them. That's what I did. And at the end, we arrived at the answer to be what? Because this is so simple and straightforward. This is vector A multiplied by minus A, negative scalar, the sense changed. This is vector A multiplied by positive scalar, the magnitude change. This is vector A divided by negative scalar, the sense change and the magnitude change. But like in this case, in which the sense has changed, what about the direction? The direction is the angle of inclination, which remains the same, irrespective of the type of scalar that you use in multiplying the vector. So that's why I said, except something happened to my sense, I couldn't have said that the answer was sense. Because the question says that multiplication of a vector by a scalar will never change the vectors. Will never change the vectors. Magnitude? No, it will change the vector's magnitude. When you multiply a vector by a scalar, it will change the magnitude as we have seen. Will never change the vector sense? No, it will change the vector sense. When you multiply with a negative scalar, the sense is reversed. Direction, will it change the vector's direction? No. It means one, you didn't go over our lecture, because it's as if I'm saying it the first time, and I know we deliberated this the last time. You have to be serious, really. Because these are things that ordinarily you should know, from your Math 106, vector algebra. So I don't need to review anything here. But because it is central to understanding the formulations that we are going to start after this review, I felt the need to really take my time and digress a bit so that I make sure that, the concepts are clear. But even having attended, if you don't go over it, review it, understand it, it will be useless. And I will understand that you haven't done anything. I will get that information. You don't need to tell me that, yeah, I read my note, I have understood everything. I will definitely understand that in class. Because that's why I even repeated the question. If not, I would have continued with the next slide. Isn't it? But I brought the same question we deliberated on. And you had the same consensus. If to say maybe one person thought of direction as the answer, okay, at least But all of you unanimously, that is not a good sign. And by the way, this is just the beginning, and the pace at which I am moving is extremely slow. And I know why I'm doing that, because at this stage you need to understand the background very well without any assumption that all is well, while I know that you may be lacking in one thing or the other. Then once the background is clear and the foundation is laid, then we will move as fast as possible. But if you don't get this basic concept clear, we are going nowhere. Sincerely speaking, we are going nowhere. Okay? Okay, so the answer to this problem is direction. The direction will not be affected when a vector is multiplied by a scalar, because direction, as we defined it, is not really the arrow. The arrow could be, because we define a vector as having three attributes: sense, direction, and magnitude. The direction is the arrowhead, pointing, showing where it is moving to. Then the direction is the angle of inclination, theta, to any reference axis, either the horizontal x-axis or the vertical y-axis. What? Yeah, the sense is the arrow. No, the sense, the direction is not the arrow. It shows the direction it is moving to. It is not the vector's direction, but it is showing whether it is moving this way or that way. But in terms of vector, when we say the vector's direction, we are referring to the angle, theta, which we clearly defined here. Clearly defined. Direction, but defined by the angle between a reference axis and the arrow's line of action, then sense by the arrowhead. And with this example, you have the direction to be 20 degrees. Okay? So that has to be very, very clear. Okay? You don't just take the arrowhead as the direction. It shows where it is moving to, because that will be affected by multiplication with a scalar. A negative scalar will change that sense, will reverse it. But no multiplication with any scalar will change the vector's direction. No. Okay? Okay. Now, we move to system of forces. When two or more than two forces of different magnitude and direction act upon a body, they constitute a system of forces. And here you have basically two concurrent forces, different forces meeting at the same point. Okay? They are called concurrent. But they don't need to have the same direction. Okay? If they have the same direction, then they are collinear. Collinear means they lie on a straight line. Okay? That's if they have the same direction. And by same direction, it means the angle of inclination. Let's say you have this, the angle is theta. You have another one. The angle for this one is also theta, right? By what we call, these are corresponding angles, isn't it? Corresponding angles are equal. So they have the same direction. Okay? So they are collinear. Okay? They are collinear. It's not necessary that they must have the same sense. Mind you, they could have opposite sense, but the direction is the same. Do you understand? Okay. So these two are collinear. They lie on a straight line. Simple, isn't it? And then you have the other type, which is the coplanar forces. Oh, the color is red. It's not showing clearly. Coplanar forces, which means is the one in which you have two or more forces that lie in the same plane. Same plane. They could be concurrent. In fact, all concurrent forces are coplanar forces. Coplanar, they lie in the same plane, the same XY plane. Now, how do you determine the resultant force? We mentioned that when you have two vectors, A and B, the resultant in vector form, isn't it? It's just the summation of the vectors, right? But this equation is applicable when you have the vectors expressed in vector form. Okay? But more often than not, you may have the vectors expressed using their magnitudes only. Like just, let's say, 10 Newton, 10 meter. Is that clear? So in that case, they have been expressed in magnitudes only. So you cannot just say you have, let's say you have this to be 10 Newton, and then you have this to be 20 Newton, and then you come here and say that the resultant vector is 20 plus 10, which is 30 Newton. No, zero. Okay? Because the vectors are expressed in magnitude, not in vector form. If they were expressed in vector form, that is when you simply add them up to get the resultant vector. Otherwise, you employ some other techniques using your knowledge of mathematics, trigonometry, and properties of parallelogram triangle. Okay, and that is where we are heading to. I think, have I started explaining the cosine rule? Before?
Let's say we are going to use it. Just talk about it.
Okay, all right. Okay, so this is wrong because these are in magnitudes. Okay, they are not in vector forms, although they are vectors, but we only have the magnitude, so we cannot just add them up to get the resultant. We have to devise another means using parallelogram law, and then we move to triangle construction. When these forces are represented in magnitude and direction, okay, or they are given in vector form, here you have system of forces, because you have more than two forces, isn't it? Right? You have more than two forces, F1, 2, and 3, and we want to find the resultant. What do? You take the first two, any two, can be F3 and F2, okay? So here we took F1 and F2, and apply the parallelogram law. But I explained the parallelogram law before, right?
Yes.
Right?
Yes.
Okay. And we discussed about the properties of parallelogram and triangle,
Yes.
right?
Yes.
Okay. So here we take any two, apply the parallelogram law, by constructing a parallelogram, and the diagonal is now the resultant, okay, which is F1 plus F2, right? And then use that resultant with the third vector, and also construct another parallelogram to get the overall resultant, which will be this one plus this one. So the resultant will be F1. So what are we saying in essence? When you have a system of forces, the resultant is just equal to the summation of all the forces. The algebraic summation of all the forces. Simple, isn't it? By that. Am I right?
Yes.
The resultant force, let me call it Fr, is just the algebraic summation of all the forces. What is the condition? Provided the vectors, the forces are presented in magnitude or in vector form, isn't it? If not, then you have to go through another way, which we are going to explain later. Is that clear? Now, we are going to expand on how do we apply the parallelogram law and the triangle construction to find the resultant vector. That is in a situation whereby the vectors are not represented in vector form, but we only have their magnitudes. Is that clear? And then we'll also look at a case whereby the vectors are presented in vector form, where we simply add them together to get the resultant. We will also look at how do we now convert, or how do we now, given a vector that is given in magnitude only, how do we represent it in its complete vector form? Okay? So these are the summary of what we are going to learn, and then at the end we will learn some vector operation like the dot product and the position vector. And then from there we move on with the business of the day. Okay? Now, determination of resultant force using trigonometry. We draw a force triangle. You remember we first draw parallelogram, okay, which divides it into two triangles, and then take any of the triangles and then analyze using trigonometry by applying either the cosine formula, isn't it? This is the sine formula and this is the cosine formula, isn't it? And we know that depending on what is given and what needs to be found, sometimes you may find the two formulas applicable for one problem, and sometimes you may find only one of them applicable. So this I don't need to go further into, okay, when do you use sine law, when do you use cosine formula, isn't it? I'm very sure this is elementary mathematics, right? Which I presuppose that you are all aware on the usage, okay? We are going to use them for some few examples, okay? You see, this will enable us find some of the sides and some of the angles. Some of the sides will constitute probably a resultant force, a resultant vector, which we may be looking for, okay? Now, these are some tips. Use the sine law when you know two angles and an opposite angle, two sides and an opposite angle. You know, use the cosine law when you know two sides and the angle between them. So this I'm pretty sure we all know. You know, C, you have cos C here, okay? A squared plus B squared minus 2AB cos C. Okay, we have a simple example here in which we have the screw eye that is subjected to two forces. You can see the screw eye. We have the directions given, isn't it? 10 degrees and 15 degrees, and then the magnitudes. So we have what it takes to represent the vector in its vector form, because we have the magnitude and direction. But then we want to demonstrate the use of the cosine and sine formula, the use of the parallelogram law in this example. Later on, we will learn how do we form the vector form from the direction and the magnitude. How do we represent the vector in its vector form? Okay, but in this case, we want to use the trigonometric method, okay, which means we'll just form our parallelogram, and then the resultant gives the diagonal, isn't it? The diagonal is represented by the resultant, isn't it? And then we do some constructions because we have two triangles. We pick this one, you can pick this one, and arrive at the same answer. But then we need to work out the angles within the triangle, okay? How do we start? This is 10, 15. So what is this angle? Total is 90, right? So it's going to be 90 minus 10 minus 15, isn't it? So this is 65. 90 minus 25, right? Simple. And then we agreed that the opposite angles are equal. So if this is 65, that is 65. Okay? Then what will be this angle? The opposite angles are equal. The total angle in a parallelogram is what? 360. So if we call this x, okay? So it's going to be 65 plus 65 plus 2x equal what? 360. So x will be 360 minus 2 times 65 over 2, which is 115. So each of these is what? 115. Okay? And then from there, the question is saying we should determine the magnitude and direction of the resultant force. So we should find the magnitude, which is Fr, and then the direction. The direction, like I always say, is the angle of inclination to any reference axis. You can find the direction with respect to the x-axis or y-axis. Up to you. Unless it is explicitly stated in the problem. Okay, but here we want to find the direction with respect to the x-axis. So, as such, what we need is this angle, isn't it? From the resultant to the x-axis, right? But for now, we need to find this angle, because this angle is known, 15, right? So we can add to theta to give us the direction of the resultant force. Okay? So now we can isolate this triangle and go and work it out to find Fr and theta. Are you following? Yes. Which is what we did here. This is 115. But we also mentioned that the diagonal does not bisect the angles, isn't it? The diagonal bisects the parallelogram into two equal triangles, but it does not bisect this angle, right? So that is why we didn't put this angle theta to be equal to 65/2. Is that clear? That is very important. Okay? So we have theta here, we have 115, and this is 150, this is 150, right? This is 100. So we have two opposite sides, and we have this. We want to find this one. What do we use? Cosine formula, isn't it? And we have this angle, isn't it? So we just apply the cosine formula to find FR, isn't it? Very simple and straightforward. And then to find theta, this one, we use the sine formula, isn't it? Which is 150 over sine theta is equal to the resultant over the sine of the angle. And theta equals this. But this theta is not the direction of the resultant force. Phi is the direction, isn't it? Because it has to be with respect to a reference axis. Okay? So phi is equal to theta plus 15, which is exactly what we did here. And you can see, even after having written the direction, we indicate. You can see a small sign here. Meaning this angle, this direction, is with respect to the x-axis. If it were to be with respect to the y-axis, it would have been this way. That this is the resultant, the direction is with respect to the y-axis. So at all times we try to do that, because I told you the direction can be with respect to the x-axis or y-axis. In some problems it may be explicitly specified. In others, just find the direction. And in that case, you are free to either find it with respect to the x-axis or y-axis. But at the end, you have to indicate this. Okay? That, okay, this direction is with respect to the x-axis or with respect to the y-axis by drawing any of these symbols. Is that clear?
Yes.
All right. Any question? No. All right. So this is another problem. This is another problem in which we have been asked to resolve a 600 pound, this is a 600 pound force into components acting along U and V axis. You can see V axis, this is U axis. And determine the magnitudes of these components. Okay? And determine the magnitudes of these components. You see, when you have U and V axis, it doesn't necessarily mean they are orthogonal. Okay? What do you mean by orthogonal? Yes. What? Orthogonal. What?
You say like you are saying.
Is it octagon?
No, it's not orthogonal. Orthogonal. It's not octagon. Orthogonal. What is this? It means they are 90 degrees. They are perpendicular. Okay? So, when we have Cartesian coordinate system, they are orthogonal. Okay? But when the axis is referred to as U and V, more often than not, they are not orthogonal. So you don't assume that the angle between them is orthogonal. And when you look at the figure clearly, you will agree with me that no, this is definitely not 90. The angle between U and V is definitely not 90 degrees, isn't it? Okay? Now, this question did not mention anything about the resultant. Okay. You see, here, as usual, we construct, because we want to find the U and V components of this force. Okay? So, as usual, we construct our parallelogram with the other sides as the sides of the parallelogram. And then work out the triangles, because this will divide it into two. And then we work it out. When we do that, this is 30, 30, right? If this is 30, and this is 180, right? This is 60. So this is what? 180 minus 60. 120, isn't it? If this is 120, this is parallel to this, right? So this is alternate angles, isn't it? So this is also 120. We are working out the angles inside the triangle, isn't it? Because if you don't do that, you will have an extremely simplified triangle that you cannot find any of the sides. Is that clear? So that's why you need to work out the angles within the triangle as much as possible. If you don't do that, you will have so many unknowns that you cannot even apply the sine or cosine rule. So your problem will be indeterminate. You cannot determine the unknowns. Is that clear? So here, if we have 30, 120, then this must be 30. The sum of angles in a triangle, 180. So we now remove this triangle over there, and then from there indicate the unknowns. This is FU and this is FV, isn't it? And then from here we can be using the same formula straightforward, isn't it? To determine the components, FU and FV. Okay? But then the question I want to ask here is, from this triangle, let me redraw it. This is FU, FV, and this is 600 pounds. Based on our knowledge of representation of a resultant force, which of the sides here represents the resultant vector? What? Please process as fast. This is early morning. You must have taken your breakfast. What? Why? So which one is the resultant? What? He was absent? FU? Why FU?
From the Pythagoras theorem.
From Pythagoras theorem?
Yes.
So the Pythagoras theorem gives us the resultant force? Were you here in the last class? Sure?
I was not.
What?
I was not.
Oh, you were not around. And did you go over our note? Or our audio recording, at least to abreast yourself of what we did in the class?
I saw it on Sunday. I
Until-
was fully engaged, so I did not know about that.
Okay. And that goes to tell you that you need to be in class every day of the class. Should you miss it for any reason, that's why we have the audio recording that could help you in updating yourself, with what transpired in the class. Because the slides alone don't talk, isn't it? And the slides are such that there are a lot of things that probably I will mention in the class which are not in the slides. So just having the slides alone, you will not be saved, as in you won't have what is needed. So, yes, why do you say F what? FV? FU. Why FU?
Has different sense with the other.
What?
Has different sense with the other.
Different sense. They all have different senses. They all have different senses. Okay, by the way, what is the condition for determining when you have any triangle consisting of vectors? What is the condition, or what are the conditions to determine which side is the resultant vector? Wait. Let me ask you. What is that condition? Can you recall? Uh-huh. Is that the only condition?
Tail to tail and head to head.
You were here in my last class. I think some are sleeping in this class. You shouldn't forget these things. And why I always emphasize, because this is a review. A review is something that you should have known before, isn't it? And here we are reviewing it, yet we need to review and review and review again. The condition which I clearly mentioned, you have tail to tail, head to head. If you can call this a formula that you may need to memorize, please do that. Tail to tail, head to head. You look at the triangle and see which one fulfills these two conditions. They must be satisfied for you to call that side a resultant vector. So even you mentioned the first one. Is it head to head or tail to tail? Tail to tail, okay. So which of these sides fulfill these two conditions? Let's analyze. Tail to tail. This is head to head. This is tail to head. This is tail to tail, okay. But here we have two vectors. Then we move on to the next condition, which is head to head. This is head to tail. No, this is head to head. Yes. So it is this side that fulfills these two criteria. Head to head, tail to tail. If you remember, I told you that you don't just look at the longest side, which is probably what misled you into thinking FU is the resultant, because it is the longest side. And I clearly told you that no, it is not always the case. It could be, but the basic rule of thumb is this. For any of the side to qualify to be the resultant vector, these two conditions have to be met. Is that clear? Okay, so in this case, this is our resultant vector. Of course, more often than not, the resultant vector, you find it to be the diagonal of the parallelogram. Okay, but this is another thing, because if you have just a triangle, you won't know which one is the diagonal, isn't it? If you have just this triangle, in fact, you may be misled into thinking that the diagonal is always the longest side. If you think that the diagonal of a parallelogram will always be the longest side, that is what will now mislead you again into thinking that the longest side of the triangle will always be the resultant. And that is not the case. It is not a rule of thumb. Okay? So if you have the parallelogram, of course, yeah, you can say that the diagonal will always be the resultant. But if you have just the triangle, then you don't have that luxury. Now you have to stick to this. Tail to tail, head to head. Don't forget this again, and trust me, I will ask this question several times, isn't it? Maybe not in this class session, but in subsequent sessions. So, if I find you wanting, if you forget it, it means you are not following us, as you should. Okay? So, I think here we are done, right? We found the components, FV and FU. Now, this is another one. You see, all we are doing here is just to demonstrate the use of the trigonometric method in finding the resultant vector, which may not be of so much importance, but at least it will make you understand the concept of resultant and how to find it. And how to find it when the vectors are expressed in vector form or when they are represented in only magnitude and direction. Because magnitude and direction alone doesn't make a vector. You need to find a systematic approach to now combining the magnitude and direction into the vector form. which we are going to learn after this. Okay? Now this is another problem which is similar to what we did before, is saying that it is required that the resultant force acting on the eye bolt in this figure be directed along the positive x-axis. You have two forces, this is F1, F100, this is F2, unknown. It is required that the resultant force will act on the x-axis, and F2 have a minimum magnitude. Determine this magnitude of F2 and angle theta and the corresponding resultant force. So we have three things to find: the magnitude of F2, the angle theta, and the resultant force. So simple, we form our parallelogram and take the triangle, isn't it? If this is 60, when you form the triangle, because this is parallel to this, so this is theta, then that is theta, right? Let me just complete it here. So if this is theta, then this is what? Theta. Because this is parallel to this, isn't it? And that is parallel to that. Is that clear? So now we remove the triangle, okay? And we remove the triangle, but don't forget we were told that F2 should be minimum. The magnitude of F2 should be minimum. How do we determine that it should be minimum? From this triangle, we can try to extend it both ways and see. If you extend it this way, it will be increasing. Because as the length increases, so the magnitude, isn't it? So if we extend this way, what about backward? Yeah, this is smaller, isn't it? This is the smallest. When you go beyond 90 degrees, it keeps on increasing. So the smallest magnitude that F2 can assume is when it is vertical. It's when the angle theta is 90, right? So theta equals 90. And then this is now right angle triangle, which you can find F2 and FR. Very straightforward. Are you following? Now, tell me, the magnitude of the resultant R of two forces, P and Q, acting at a point at an angle alpha is given as what? B. P and Q. Any contrary opinion? You?
I said B.
Oh, you said B also. What about you? Oh. Still processing? Huh? B. This is the simple cosine formula, isn't it?
Yes.
Which is B. Okay. We are done with this slide. Now we move to the next one. So, I hope you are following the discussion very well. Okay? We're moving gradually. Like I said, the next presentation after this review, you will see the real application of all this to our own groundwater modeling parameters and what have you. So I could not just assume that, all this is very clear with you without reviewing them. But now, once we are done with the review and start, the other aspect, you will see why we need to take our time out and review this thoroughly. Okay? Now we move on with the review number 2, which is addition of coplanar forces. And here we want to resolve a force into its rectangular components and to express the forces using scalar notation and using Cartesian vector notation. And to determine the resultant, the orientation, that is the direction. When we say orientation, we mean the direction. Okay? And to determine the magnitude and orientation of resultant of the coplanar forces, and to express the resultant force using scalar notation and Cartesian vector notation. So, rectangular coordinates or rectangular components. When you have a force F along x and y, it has component Fx along x and Fy along y. And applying our parallelogram rule, which we learned before, isn't it? Construct parallelogram, the resultant, this forms the resultant force, isn't it? And which is given as the sum of its component, Fx and Fy. These are in vector forms. That's why they are bold. You remember we have learned the representation of the vectors, isn't it? So these are written in vector form, meaning in writing, you should write arrow on top. Okay? This is very important. Yeah, even if you change, you tilt the coordinates, it's the same thing. F prime is given by F prime x plus F prime y. Okay? And then scalar notation. X and y axis are designated positive and negative. And the components of forces expressed as algebraic scalars. This is the vector form. When you have a force F whose direction is theta, it will have component Fx and Fy, isn't it? And F is equal to the sum of its component, isn't it? In vector form. That is the vector notation. Not notation here, but representation. And then their magnitudes can be defined as Fx, the vector Fx. No, let me not say the vector Fx. Now we want to use the scalar notation. When you have a vector F, it has component Fx and Fy. Here we want to use our knowledge of trigonometry, just as we used before in trying to find the resultant force using the sine and cosine rule. Here this is 90 degrees, right? And this is Fx, Fy. Okay? So we can find this is F in scalar notation now. This is theta. So when we resolve this horizontally, what do we have? We have Fx, which is equal to what? Which will be given because when you take cos, you have adjacent over hypotenuse, isn't it? The adjacent is Fx over hypotenuse, and this is equal to what? Cos theta. So Fx is equal to F cos theta, right? Similarly, Fy will be equal to what? F sin theta. These are the scalar notation, the magnitudes. These are not vectors. They are not in vector form. Are you following? But then what about if the angle of inclination? Because the angle, like I said, can be either horizontal or vertical, inclined to the horizontal axis or to the vertical axis. So if it is given this way, what will be my Fx and Fy? Fx will now be sine alpha, right? And Fy will be what? Cos alpha. Is that clear? Because all you need to do is to construct your triangle, and then you see what will be, because this will now be Fx, right? And then you will see that it will be F sine alpha. Is that clear? Yes. Are you referring to this one?
Yes. Assuming Fs is 2, Fy is 3 in vector form, means the resultant equal to 5 in vector form.
We will learn how to add vectors. Yeah, we will learn how to add the vectors. But just like you mentioned, if they're in vector forms, yes, we will simply add them. But how is that addition carried out? We are going to learn that. Okay? But you simply add them up based on certain rules. Okay? So these are the scalar components. Now, the direction of a vector can be defined in two ways, in 2D. Either directly as it is, given the angle, or using a sloped triangle. You can see this sloped triangle with the sides given A, B, at least two sides, because you can use Pythagoras to find any of the remaining side. So at least A and B will be given, and then the last side C can be found using Pythagoras. So the direction of the vector can be defined using theta or sloped triangle. From the sloped triangle, if you want to find theta, you can do that, isn't it? Because like in this case, if you want, you call this theta is equal to this, isn't it? Am I right? These sides are known, so you can use your SOHCAHTOA to find the angle, isn't it? That is, if you still want to maintain this way. But then you can just continue with the sides without necessarily having to find the angle. How do you do that? You use the concept of similar triangle. Okay? You employ the concept of similar triangle. This is a concept that is well known, isn't it? When you have a triangle and you have another one. This big triangle, let me say A, B, C. These are the sides of the big triangle. Then you have this small triangle, D, E, F. But you can see they have one thing in common. This angle, isn't it? For this angle is the same as that one. Okay? So now, if you want to take cos theta. Cos theta for the small triangle will be what? E over what? F. And for the bigger triangle, it will be what? It will be what? B over A. Right? So can you see E over F is equal to B over A. So this is the concept of the triangles, that the corresponding sides are proportional. And not only E and F, you can take D and E. D over E will be equal to C over what? B. Are you following? So this is the basis of using the similar triangle concept. Okay? And it's also the basis that we are going to use it here. Because here we have this small triangle and that big triangle. The angle here are the same, isn't it? The angle here are what? The same. Okay? So also the corresponding sides. In this case, if we want to find fx, so this is fx, right? So fx over f is equal to a over what? C. Fx over f is equal to a over c, isn't it? If it's fy over f is equal to b over c. Are you following? So from there we can make fx the subject of the formula, which will be f into a over c or f into b over c. Minus because this is negative y-axis. So that's why here is going to be minus fy. This one. Because it's pointing towards the negative y-axis. So it's supposed to be minus fy. So the minus is for fy, which is now transferred to the other side. Are you following? So you see here, we have two ways of the scalar notation, of expressing the vector components as using the scalar notation. Either to use the direction, the angle given, isn't it? And express as either f cos theta or f sin theta. Or if we have the sloped triangle, we can still express it f into a over c. All these are the sides, or b over c. Are you following? Yes. Now let's move on. And before we move on, let's take 5 minutes break. Okay? Yes, our lecture continues. So, what we have learned so far is the scalar notation or scalar expressions of vectors, isn't it? In the Cartesian coordinate system, x, y, z. For now, x, y, before we move to the 3D system. Okay? Now we will try to learn how do we now express a vector in its vector form. That is the Cartesian vector notation of forces. But first we'll introduce something called the Cartesian unit vectors. The components of a force may also be expressed in terms of Cartesian unit vectors, I, j, k, in the direction of the x, y, and z axis respectively. Cartesian unit vectors have dimensionless magnitude of unity, as they are called unit vectors. Their magnitude is unity, 1, and they are dimensionless. Okay? So, what purpose do they serve? They are dimensionless, and their magnitude is 1. They serve to indicate the direction of the Cartesian axis. Okay? They serve to indicate the direction of the Cartesian axis. Signs of Cartesian unit vectors ijk will be described analytically by a plus or minus sign, depending on whether they are pointing along the positive or the negative x-axis. What are we saying in essence? When you have xy axis, the direction of the x-axis is described using a unit vector called I. It's a vector. For y, we use j. For negative x, we use minus I, isn't it? For negative y, we use minus j. Okay? These are vectors describing the direction of the axis. Okay? For example, the forces F and F prime may be expressed as Cartesian vectors as follows. Here you have a force, F. Okay? We say that this force vector will have component along x and y, isn't it? Okay? It will have component along x and y. This is a vector. It will have a component along x and y, right? But then how do we define the components in terms of their scalars? Because a vector is just like a product of magnitude. You have magnitude and direction, isn't it? Any vector can just be represented as magnitude, isn't it? And then you have what? Direction. Okay? The scalar component of fx is what? Fx, which we defined before, right? Either using the angle as f cos theta or using the slope triangle, isn't it? So this is scalar. Then we need the direction, which is the direction of the x-axis, I. This is a vector. Just because you don't have the arrow, no. Or sometimes in writing, we write cap above it. But sometimes it's not even, you don't even write anything, because whenever you see ijk, they are vectors. Simple. Whether you indicate or you don't. So more often than not, in writing, we don't even indicate. Because once you see ijk, they are vectors, not scalars. Is that clear? So the component of this force vector along the x-axis is given by the scalar component and the direction. And hence, these constitute the vector. You have magnitude and direction. Am I right? The same thing with the y-axis. The vector component along the y-axis, it will be described by the scalar component fy and j. And then when you sum these two up, f will now be expressed as what? Fxi plus fyj. Much the same way, as when you have a vector, isn't it? It's equal to the sum of its components, isn't it? Right? And then when you substitute, this is fxi plus fyj. So this is the Cartesian vector representation. Is that clear? And fx and fy are all what? Scalars. Meaning they are numbers, isn't it? Which you can fit into the equation, isn't it? Now, even when you tilt the axis, f prime is still the summation, but this is minus, so that's why you have minus j. So it becomes minus here. Okay? Now, resultant of coplanar forces. You have coplanar force here, or coplanar forces, which are concurrent, because they all meet at a point. F1, F2, F3. How do we find the resultant of these coplanar forces? Okay? To do that, we know that each of these forces will have component along x and y, isn't it? F1, you will have F1x and F1y, isn't it? F2 will have minus F2x and F2y. F3 will have minus F3y and F3x, isn't it? So we sum these components because it means we will have like resultant horizontal forces, because when we sum all the horizontal forces, we will have one, and resultant vertical forces. So this is just what I mentioned. This will have component here, the same thing with this one, And then we try to find the resultant horizontal force by summing all the horizontal components, and resultant vertical force by summing all the vertical components algebraically, taking care of their signs, right? This is the resultant horizontal force, FRX, by summing all the horizontal forces. Here you have, what do you have? F1x plus F3x minus F2x, isn't it? For the vertical forces, you have F2y plus F1y minus F3y, isn't it? And then, this is using the scalar notation, isn't it? What about using the vector notation? Using the vector notation, it means first we need to express F1, F2, F3 using the Cartesian vectors, isn't it? Meaning F1 will be what? In the Cartesian vector form. What? F1x I plus what? F2
F1Y.
F1y J. Good. What about F2? Similarly for F2 and F3, right? It will now be F2y, F2x, isn't it? And then we now sum it up. Are you following? This is exactly what we did. F1 is F1xi plus F1yj. F2, this is minus because it's pointing towards the negative x direction. F3, this is minus because it's pointing towards the negative y direction. And then F1, F2, F3 have all been expressed in vector form. So how do we find the resultant? So in this case, since they are in vector form, so we use the simplest way, which is just finding the summation. And how do we sum? It would be like terms. If you remember, you are saying 2 and 3. Is the resultant going to be just 5? I said something like that, but based on certain rules. Because when you express a vector in its vector form, more often than not, you will have the ijk components. At least one, because a vector can be along any of the axes. In that case, the other components will be missing. Okay? But you'll have at least one. So you sum in like terms. The i's component, the j's component, and the k's component, if it is a 3D case. In this case, it's a 2D case. So you can see all the i's together and the j's together. Isn't it? I, J. And if you look at this is the same thing as the resultant horizontal force. This is the same thing as the resultant vertical force. Are you following? If we will have them in numbers. If you have them in numbers, then at the end, the resultant force will be a number I plus another number J. If it's a 3D problem, it will be plus another number K. Is that clear? And probably you will say that is simpler than using the trigonometric method and what have you. But like I said, this all depends, because even where we use the trigonometric method, okay, I will go back to it later. We may decide to use the Cartesian vector notation, but the first thing we should do is to now to convert the vectors from scalars to vector forms. And then we apply the simple formula for finding the resultant by summing them up. What am I saying? I think it was in the other slide, in which we have two vectors, right? Then we use the parallelogram law and the triangle construction. What I'm saying is that in those cases, we can use another method, and that method is using the Cartesian vector form. Those forces, we first express them using the Cartesian vector form, something like this. And once we do that, then we can simply add them up to get the resultant. But then what we are going to learn in this slide and the subsequent ones is how do we now convert a vector from the magnitude or the magnitude and direction into its Cartesian vector form. And one of the method is this one, isn't it? Using its component. Okay? Its component along the x and y axis. Because we know how to find f1x using the scalars, isn't it? We know how to find f1x, which is what? F cos theta, as the case may be. And this one, f sine theta. Is that clear?
Yes.
So this is one of the methods to be used to form the Cartesian vector form of any vector. So what are we saying in essence? You see, this resultant vector is reduced into resultant horizontal force and resultant vertical force, which will be something like this, isn't it? Because this is positive, depending on whether, because it depends on what we have as the numbers. When we plug in the numbers, that will determine whether they will remain as positive or some will be negative. We are going to have some examples to demonstrate this, okay? But in this case, if they all remain as positive, then it means you have one vector here, isn't it, and another here, and now this is the resultant. And this is the angle of the resultant vector. And here, to find the resultant vector, using the scalar notation, you can just use the Pythagoras, isn't it? These are scalars. These are scalars, okay? Because using the vector from here, you are done. Except if you are asked to find the magnitude of the resultant vector. If you're asked to find the magnitude, then even having found the resultant vector, you have to go a step further, which is this one, to find the magnitude. You take out the coefficients of i's and j's and square them all inside a bracket. Sorry, all inside a square root, which is this one. To find the direction of the resultant vector, from here, you take tan, isn't it? Tan is opposite over adjacent, which will be FRY over FRX. Here we use modulus because we must have taken care of the signs. What do I use by, just a minute. What do I mean by we must have taken care of the signs? In actual problem, as we are going to see, FRY, so FRY could be negative, FRX could be positive. And then the resultant is going to point this way, right? Then we are looking for this angle. So we have taken care of either the positive or negative sign already. So that's why in this case we are using the modulus. So we don't carry out, if this is negative, we don't carry it over and put minus FRY over FRX. Because that negative sign has been taken care of. Instead of pointing upward, it is pointing downward. Done. And that is very important. Yeah, what's your question?
In this case now, we need to take into cognizance our condition for finding results and head-to-head, tail-to-tail. Because it seems like it's not going to be applicable.
It's going to be applicable. Why? Okay. You have FRX here, right? FRY here. And you have the resultant here, right? Okay, if you complete your parallelogram, this FRY, this is also FRY. This is FRX, this is also FRX. So if you take any of this triangle, any of them, and redraw it, what do you have? This is FRX, this is the direction, this is the resultant, FR, and this is FRY. So which one is the resultant based on the rule? Is the condition satisfied? And the same thing will happen when you take the upper one. Are you following? Okay. Now, okay, let's take some examples. Here we have a boom, and we're asked to determine the components, x and y components of F1 and F2, and express each force as a Cartesian vector. Cartesian because we have xy. We have different coordinates, Cartesian coordinates, we have Euclidean coordinate, polar coordinate, and what have you, isn't it? Cartesian coordinates, you have the xy, isn't it? Which is the coordinate that we normally operate on, except for the electrical engineers, in which they can have the complex space and what have you. But more often than not, the Cartesian coordinate it satisfies our need. Okay? So, you have F1, 200 Newton, and the angle of inclination 30. You have F2, 260, and the direction is given by the sloped triangle. Can you see that? We are asked to find the Cartesian vector form, to express each force, to find the components, because this will have component vertically and horizontally. This one will have vertically and horizontally, isn't it? And then we find the Cartesian vector form Very simple. This angle is to the vertical. So what will be the vertical component of F1? Oh, that guy is sleeping. I caught you. Haven't you slept last night? Or do you have test today? So F1, what will be F1y, the component of F1? What? The component, the scalar component. What? 200 sine theta? The vertical is cos theta. The angle of inclination is to the vertical, isn't it? So it's going to be cos theta. And the horizontal component will be sine theta, right? And then the vector will be expressed in vector form as F1 equal 200 cos theta j minus 200 sine theta I. Minus because this will be towards the negative x direction. Are you following? And what is exactly what we have here? F1 minus 100I plus 173J. And this 100 and 173 is obtained by taking the scalar component. For F1 you can see minus 200 sine 30, which is x. Then plus 200 cos 30, which is y. Are you following? We do the same thing for F2, except that here we have the slope triangle, so we have to use similar triangle. So for Fx, F2x is going to be what? F2 into 12 over 13, isn't it? For Fy, it's going to be minus because it's towards the negative y-axis. Okay? So it's going to be minus 260 into 5 over what? 13, which is exactly what we have, isn't it? This for F2y. But mind you, when we come to put it in the vector, it has to be negative. Are you following? Now, let's move a step further, just with this one. What about if we want to find the resultant force? Because the question did not ask us about finding the resultant force, isn't it? What about if we want to find the resultant force here? How do we go about it? What? Which we did already. So how do we find the resultant force? We sum what? What do we sum?
The vertical and horizontal.
How?
Algebra. We solve it algebraic.
What? You don't just say we sum the horizontal. The Cartesian, we already formed the vector forms, isn't it? F1 and F2 have been represented in vector form, isn't it? In the Cartesian vector form. So the resultant force, it will just be F1 plus F2 in vector form, in the Cartesian vector form. So now we'll just sum this one up. And what do we have? 140I and then plus 73J. Do you understand? If we want to find the magnitude of the resultant force, which is FR, isn't it? The magnitude will be square root of 140 squared plus 73 squared. Am I right? What about the direction of the resultant force? It's going to be the tan inverse of FRY 73 over what? FRX 140. And don't forget, it should be modulus, isn't it? Although none is negative here. Are you following? Do you understand? So, do you see how simple it is to find the resultant force when the forces are expressed in the Cartesian vector form? Mike, can we still find the resultant using our first method? Using the parallelogram law and the triangle construction? Yeah? We can still find the resultant, isn't it? By drawing our parallelogram, isn't it? The resultant will be probably something like this, and then we draw our parallelogram, isn't it? And then we find the angles, the inner angles, and then we go by the first method. Is that clear? And that's why, like I told you, we will now learn the different methods of finding the Cartesian vector form of vectors. This is one of them. isn't it? There are other methods which we are going to learn. Now, this is another problem. The problem is, you see all this, probably you should have learnt it in statics, the CVN 201. But probably the syllabus may need to be modified. Because all these lectures is from the statics, the CVN 201 course. All this. So just imagine maybe you have learnt it there. So my course would have been very easy going and what have you. But now you two are having a lot of tough time, isn't it? Trying to process, internalize, understand. But it's something that should have been taught under statics. But we will see what will happen, except that although it is not our course, and to be candid, for any numerical modeling, you need to understand this concept clearly. Because once we start the modeling, things will be expressed either in matrices, in vectors, and these operations, are what will become the order of the day. And once you don't have very sound background, then you will just be looking as if some magic is being performed. Now, here we have a boom, which is acted upon by 3 concurrent and coplanar forces, F1, F2, F3. We are to determine the magnitude and orientation of the resultant force. So first thing you need to understand, the magnitude, it means the scalar component, the scalar form of the resultant force, and the direction, which is the angle, isn't it? So it means you can do it in 2 ways. You can still do it using our first method, the parallelogram rule and the triangle construction. But that will take a lot of time, most especially in this case when you have 3 forces. Because it means you will first take maybe the first 2, apply the rule, get the triangle, get the resultant, and then apply it with the third one. That will take a lot of your time. So the simplest method is to find the Cartesian vector form of the vectors, and then follow the simple approach by simply adding them together, component-wise. Is that clear? And then you can get the magnitude and the... Oh.
No, no sleep.
Then you should look at the board. If you are not sleeping, except if you are meditating, and this is not the time for meditation. Look at the board. While in the class, your eyes have to be fixated on the board. Okay? So now, as we did before, F1 will have only component horizontally. So when expressing it in Cartesian vector form, it will just be what? Minus 400i. Simple. Because it will have no vertical component. All of you are using your phones. I think initially, I was saying this is is the material. So why don't you want to look at the board? Huh? Are you also looking at the material from the board, from the phone? And that one is not the material. He's chatting or doing something else, right? Please, while in the class, you see, we are supposed to have just 1 hour, but we missed a lot of classes before. That's why we made it 2 hours this week and probably next week also, because we have a lot of things to cover. Okay? While in the class, I will suggest we be attentive. If you are feeling sleepy, you can go out and wash your face. Okay? Put water, so that you'll be alert. Okay? Or stand up and stretch, left and right, stroll. And that's why we normally have, if it's 2-hour lecture, we give 5 minutes, 10 minutes break, so that you can walk around and so that your level of alertness will be enhanced. Okay? But it's very important while in the class, you put aside your cell phones, except maybe those that are opening the slides. Put aside your cell phones and concentrate so that you get the message. You have all the remaining hours, to chat, to gist, to play around as you please. Okay? But while in the class, You need to be attentive, very, very attentive. Now, for F1, the Cartesian vector form will simply be minus 400i, because no component vertically, isn't it? For F2, we have the angle, isn't it? It will be what? 250. Yeah, tell me. For F2, complete. Let's start with horizontal, then vertical. No, in Cartesian vector form. So just tell me the expression for F2. For F2, it will be what? 250 cos 45. You are still having problem with sine cos, and that is very, very important. You need to open your eyes and see that clearly the angle of inclination. Is it inclined to the horizontal or vertical? And then think about the appropriate changes that accompany whether it's inclined to the horizontal or vertical. That's very important. Because once you don't get the Cartesian vector form correctly, every other thing is going to be, the step could be correct, but the answers will be wrong. Yeah.
With regard to this, even though it's a kind of course is the same, because even though...
Yeah, this is just for 45, but in some instances, it's not 45. Like this is 345, the angle is not 45. Yeah, for this one, if you interchange them, you will arrive at the same answer. You will just be lucky because the angle here is 45. But any other angle, the story is going to change. So, what is going to be my F2? Now tell me.
250.
Yeah?
Sine 45. Plus...
No, what about the Cartesian unit vector? I?
Plus 250 cos 45.
J, good. What about 200? F3? Yeah.
200 minus 200.
Minus 2. Oh no, you told me now. I don't want to hear you. Now, my friend.
What am I carrying now?
Yes, I want you to tell me the Cartesian vector form of F3.
We have minus 200.
Good.
That will be vertical now. It's going to be close.
F3.
Okay, the horizontal, sorry.
Okay.
Minus 200 cos.
Cos. Oh. He was sleeping when we taught the sloped triangle method. Were you sleeping? Okay, the last person there. Yes. Give us F3. This is 4. 3, 4, 5. The triangle is 3, 4, 5. 4 over 5. Go ahead. So minus 200 into 4 over 5. No, I want the Cartesian vector form, the complete. I. Go ahead. 200.
Yes, 200.
Yes, go ahead. That's all? You just told me the horizontal component. Are you saying the first F3 will not have a vertical component? Then what is the vertical component? Okay. What? You just told me that of x-axis. With sine, this slope triangle. Huh? 3 over 5, J. Are you all following? And for F1, we said it will be what? Minus 400i. So you see, the main task here is in converting the vector from its magnitude to the Cartesian vector form. Once we express them in Cartesian vector form, then the remaining, problem will be very easy. I mean, to find the resultant now, we just sum them up component-wise, and to find the magnitude, we use the formula. To find the angle, we use the formula. And this is exactly what we have been saying, isn't it? Oh, here, okay. Here we found the sum of the horizontal forces, because the question is asking us only to determine the magnitude and orientation of the resultant force. And we know in the formula, the resultant force, the magnitude is given by the square of Frx and Fry. So in this case, we just found Fry and Frx, the summation of the components, which you will also do from the vector forms, from the Cartesian vector forms. So this is the summation of Frx and Fry. And then we substitute in the formula. And then to find the direction is tan inverse of Fry over Frx. But don't forget, we don't use the sign. You can see Frx is minus, right? But we don't put the minus here, because the minus has been taken care of in this figure. This is Fry, this is Frx, and this is the angle for the resultant force. And that's why when finding the direction, here we don't use the sign, because we mentioned that the magnitude of a vector quantity is always a positive number, isn't it? The magnitude of a vector quantity is always a positive number. And that's why here, since we took care of the sign, so it becomes plus 382, but directed along the negative x-axis. Is that clear? But the magnitude is always a positive number. Are you following?
What about if someone put the minus sign, but put it in the modulo?
What?
When you put it in modulo, you put the minus sign, you put it in modulo. Is it the same thing?
Yeah, it's the same thing, because it means you will ignore the minus sign. And that's why in the formula it is giving as modulus.
Now, which one is the orientation? Is it the modulo?
Oh, I passed it. Okay. So in the formula, that's why we have the modulus, so that should you even put it there, you don't use it, because the modulus is to make it positive. Is that clear?
Which one is the orientation?
Yeah, that's the direction. Yeah. Orientation, direction, synonymous. Okay? Are you following? All right, now get a paper. Yeah. Time for you to work. I have done my own part. Now it's for you to find the magnitude and resultant of these two forces, F1 and F2. And fortunately for you, they have all been expressed in vector form. Isn't it? So, very simple, straightforward. You are to find the magnitude and resultant of the two forces. The magnitude of the resultant of the two forces. Once you are done, let me know so that I can come and inspect. Yes. Done? Oh. Okay. Who else? Okay. Show me. Okay. Oh, your calculator is, it needs to be re-energized. Yes, yes, who else? Done? Think, check this. Then how did you arrive at this?
I summed them.
Show the step.
I showed you. This summation of this 20 high.
How did you get this value?
Okay.
How?
I summed them.
Somewhat. Hmm?
I will see.
Okay. Okay.
This is the resultant. This is the
Maybe we need to work this out again.
okay, but the procedure is right.
Yeah, looks right.
Okay.
Seems right. Yes. Okay. Done? Yes, 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 yes. Who else? Done? Hmm?
I'm fine with it.
Yes, yes, yes. You have 1 more minute. Just 60 seconds to finish. Done? Okay. You know why?
Unit.
Unit is very important. We don't forgive when you miss the unit. Okay. What about yours? Hmm? Hook where? And then find the magnitude of the resultant force. This is the resultant force. Then get the magnitude. That's what the question is saying. Get the magnitude out. Yes, you have 10 seconds. 10 more seconds. Just 10 more seconds to go. 10 more seconds. I don't know what you are still doing.
Yeah, I've gotten it.
Then what is the answer? No, you didn't punch. You are just no.
I've punched it.
No, punch it. Punch it. I was just looking at the option and I saw when you look at what did you show him?
I asked him something.
Eh?
I asked him a question.
No, you don't ask. When I give you classwork, you don't ask anybody.
Okay.
You have to do it independently. No communication, no giraffing, no nothing. Okay? You don't ask anybody anything. Who else? Did you finish? Have I checked it? Okay. Yes, yes. Are you done?
I'm still on it.
Okay. Because you have just 1 second. You have just 1 second to go. So I think Okay, so we all got it right, and what we simply do is to sum F1 and F2 component-wise, isn't it?
Yes, sir.
And then we find the magnitude by squaring the coefficients of ijk all in square root. Very simple, straightforward, and direct. Because here it's straightforward because F1 and F2 have already been expressed in vector form, Cartesian vector forms. Now, the next one. The direction of the force, F, from the positive x-axis is what? We want to find the direction of this force, F, from the positive x-axis. You have 3 minutes, no more, no less. I have started counting now. This is 50 seconds. So exactly 3 minutes. We want to find the direction of this force from the positive x-axis. Done? Okay. 6, 10, 15.
Sir.
Oh, sorry. Okay. But if you can represent it before finding it, I will appreciate it. Represent the vector F in x and y axis. Represent it. Show it. Okay? Yes.
Positive.
Yeah, then why is the force? F. Yeah. Yes. Show me the force in 2D. In XY axis. Yeah, show me the force in XY axis. Show me the force in XY axis. What? No. Show me the force in XY axis. No. Where is the force? And where is F? And where is F? No. Check it again.
Okay. Sir.
Yeah. Because you need to have a feel, you need to be able to represent the vectors pictorially in XY coordinate. Okay? Where is the angle?
Okay.
Show me the angle in the figure. Indicate. Good. Okay. No. You said this is 50. The x coordinate. This is minus 50. Three minutes is almost, this is almost 3 minutes now.
Done.
Where is the representation? This is what?
50.
But that is minus 50.
Okay, it's done.
Then do it correctly. Yes. Did you show me yours? Okay. Did I check yours?
No, sir.
Okay. Are you done? You have just 5 seconds. 5 more seconds. Where's the angle? From the positive x-axis. It says from the positive x-axis. Good. Indicate, right? These are there. Done? Yeah. Representation. And why is F? Why is F?
F.
Yes.
This one.
No. Why is F? F is equal to this. Why is your F? No, not the writing, but indication here. You didn't indicate it here. No. That should not be F. Good. Because it is F that has a component here and here. The direction. The sense of F. The sense. And theta. The direction of F. Okay. Done? What is it? Okay, and the representation?
This is 60 I.
But you didn't indicate, you just put X, just represent it fully.
I'm just corrected. I'm just trying to have it clear.
Yeah, but do that as very, okay, done?
Yes.
And why is theta?
Theta is 9.8 degrees.
Where? Inclined to the vertical? From the positive x-axis. From the positive x-axis. Are you sketching?
It's not a sketch.
No, you just write theta here, simple. And okay, yeah, just write theta here from the x-axis to the vector. Yeah. I think you are all done, right? Then why is the force F?
We say that magnitude only.
No, I asked you to represent the force F.
Representation.
No, why is F?
That is resultant.
No, F. Why is F?
Okay, F is here.
Where?
Okay.
In the diagram, why is F?
Resultant?
No, I say F. Here I only have one force, right?
Yes.
So why is F in the diagram? Here you show me the components of F, right?
Yeah,
So why is F?
it's here.
No.
Okay, it's here.
Then sketch it.
Okay.
And why is theta?
Theta is
Why is the sense of F?
coming there. Theta is here. Opposite all over. So here is theta.
Okay, then write it. And what is the sense of F? Show the sense for F.
Result arrow. Okay.
Sense. Okay. So I think some of you got it straight away, but some with some difficulty. But at the end, we all got it because we need to be able to represent vectors in XY coordinate system. F equals 60I minus 50J. It means the component Fx is 60, isn't it? Fy is minus 50. Some of you put it here, but this is minus, so this is 50. And then the first F, some just cross it this way. It is the result, so it has to start here. It is later when you apply the parallelogram law that when you have the triangle, but you don't just start with the triangle. That is one thing when using even the first method. You don't start with the triangle. You start with parallelogram construction first, before you now extract your triangle from the parallelogram. So this is now F, and the angle, it says from the positive x-axis. So this is the correct representation of the vector F. Okay, this is x, y. Is that clear?
Sir,
Yes.
supposing the direction was asked from the negative x-axis.
From the
Negative x-axis.
negative x-axis, which is this one, right? It may never be asked because it shouldn't be there. It is here. So it could be asked from either the positive x-axis or the negative y-axis, because it belongs to this quadrant. Is that clear? So any question before we call it a day? No question? So in the next class tomorrow at 8 as well, but please be here on time. Be here on time so that we can start on time. Okay, we have just 2 hours. Probably, I don't know, maybe tomorrow, if time permits, we may be done with the review. Okay, hopefully, because I have review number 3 and 4 as well. But hopefully, we may be able to finish all the reviews tomorrow.